Okay, somebody sent me an email and asked if there was a practice test 4, and I said, yeah, there are 2 of them in Canvas. There's only one. I didn't realize. I knew I had 2 files here. This is the old test, and here are my solutions. So there is a practice test. Just had a question about first question in the homework. Okay. What was your question about it?
Well, I started doing it like the day before yesterday, and I just got stuck throughout the process. So I was reading through some of the materials before I tried it again. So I was just hoping we could just kind of go over it.
Oh, so you like wanted me to go through it?
Yeah, if it's possible.
When is this due?
The 18th.
Okay, we still got a couple more days. We only have 3 questions in the homework. Wow, that one's complicated, isn't it? Huh. I don't know if I realized this one. I think somebody changed this question. Yeah, I don't remember this third one being this nasty. I'm going to look at the homework, and if a bunch of people have already done it, then I can't change it. But if not, if nobody has done this problem, I might change this problem out. I mean, it's not like it's impossible. It's just going to be quite a few steps. Somebody says it took me over an hour. It was so long. Yeah, I can imagine. This is a nasty one. This was not the problem I had when I built the homework. Maybe I'll turn that one into extra credit. Yeah, let's do that. I'll make this an extra credit. That's fine. So here, yeah, I can kind of get you started on this problem. Library, and let's start a new one. Okay, what do we have? Y double prime, xy prime minus 4y. I literally already forgot what it was. Plus xy prime minus 4y equals 0. Okay, so we're going to start like always. Y equals the sum, n equals 0 to infinity, a n x to the n. It means y prime. N equals 0 to infinity, a n n x to the n minus 1. Now the first term here is 0 at n equals 0, but because I've got this x sitting here that's going to distribute in, that's going to bring this power up to x to the n. I don't want to play that game, even though it's true that I could start my sum here at 1. This is a true statement. I'm not going to do this. I'm not going to use that because I've got this x here. And then y double prime will be the sum from n equals 0 to infinity, a n times n minus 1, x to the n minus 2. This guy doesn't have anybody in front of him, and the first 2 terms are 0. So I am, that's a 0 right there. It doesn't look like it. I am going to go ahead and fix this by raising all these up by 2. Well, first, the first two terms are 0. So I could, if I wanted to, just start counting at 2, since the first 2 were 0 anyways. And then I could raise all these up by 2 and drop him down by 2. And I forgot to do all that. Hold on. I said I was going to do it, and then I didn't do it. Drop this down by 2, raise all these up by 2. N minus 1 plus 2 would be n plus 1, and then I'll have an x to the n here. So then my dE will become y double prime, so that thing I just wrote, starting at 0, plus x times y prime. So I'm going to head and do that. I'm going to take this x and distribute it across the sum. I'm allowed to do that because this sum is absolutely convergent. That's our assumption. So x to the n minus 1 times another x will give me an x to the n. I have the n right there. And then minus 4 times the original. So I'm going to put that minus 4 inside the sum. There's a negative 4 an x to the n. This is supposed to equal 0. Because that's what I have over here, equals 0. Then I can squish all these together because all my powers are in. All my indices start at 0. So here's my recursive formula. Which, of course, I would probably want to isolate this guy here, move all this stuff to the other side, divide by these, and so forth. And then once you get there, we're just finding the first few coefficients. And remember, anytime you have a second order dE, A0 and A1 are free. If you're solving an IVP, that's what these are. This is A0. Y of 0 is A0. Always, every single time. As long as we're expanding about x equals 0. So here, that's the assumption. We're expanding about the point x equals 0. So y of 0 is always A0. And y prime of 0 is A1. Again, if we're expanding about x equals 0. And they give us both of those, 1 and 3. So these I know, A0 is 1, A1 is 3. We just have to find 3 more terms using this recursive formula. Okay, does that help?
Yeah. And so once we write it in the form of a sub n plus 2 equals etc. Plug in n through however many terms are needed. Depending on the pattern, we divide it into odds and evens.
No, it doesn't have us dividing anything here. We're just finding the next 3 where n equals 0, n equals 1, and n equals 2. We're just getting numbers. Okay. And then we're done.
Gotcha.
See, it doesn't even have us here separating out the A0 terms, the A1 terms. It doesn't ask for it, so we're not going to bother.
Okay.
Okay, here, this is just asking us to go through that trouble and then kind of separate out the terms. Yeah, I think somebody changed this question too. I don't remember this question being like this. Okay, if we have time, maybe I'll go through like a starting on both of these questions. Okay, so we've got test 4 coming up and our project coming up. We need to be thinking about both of those. So here's an old exam. Your test is going to be kind of similar to this. I think I've downloaded this 4 times now today. So, writing out a couple of power series. This one does, in fact, ask us to separate out the terms, get all the terms with A0. That may or may not be even and odd powers. Sometimes it works that way, sometimes it doesn't. Sometimes you'll have 3 in a row that have an A0 and then 3 in a row that have an A1. You just have to write out a bunch of terms. You may not even see a pattern. Here we're doing Euler's formula. My recommendation to you is do it by hand because that's what we're asked to do here, but then check it in Excel. Here we're sketching a direction field. On your actual test, I tell you on this old test, I just let them pick random points. And remember, we have these direction field graphers, also called slope field generators. If I remember right, the GeoGebra one I like better. I've got too many windows open here. So, I mean, I can see what it looks. Oh, look, that's the one that it has in there naturally. Like that's the default is X plus Y, the one I'd put on the test. So what I had them do in previous semesters, just pick a whole bunch of random points, plug in a point, say the point 3, 5. X equals 3, Y equals 5. My derivative at that point would be 3 plus 5. That would be 8. So at the point 3, 5, I would put in a little unit vector with slope of 8. What about the point -2, 1? -2 plus 1 would be -1. So at the point -2, 1, I would have a slope of -1. And we'd do a whole bunch of those. And then if I wanted to find one of my solution curves, I would just pick a starting point. Oh, wait. So say I wanted to start at the point -2, 1. And I would just follow all my little vectors and plot out what a curve. Think of this like a current, like you're watching little current lines flow through a river and you drop a boat in right there at that spot. That's going to follow along these lines. It's going to follow this current. If I drop my boat in over here, it's going to go this way. So I'm going to have you do something like that on the test, only I'm going to tell you a whole bunch of points along a curve, like points that I specifically picked out. And then I want you to compare what you get with the actual solution because it's one you can actually solve. Here's another power series. And then this was a really good problem. This is what I used for the basis of this document here to help you prepare for project 2. So the idea behind the problem is, we're going to look at this DE. This may look familiar to you. This is that one I posted as an extra credit discussion where the guy solved it 5 different ways. And you know what's funny is I looked through all those discussions and everybody was like, wow, that's amazing that we could solve this one. I've done that. Throughout the semester, I have literally solved this problem, all 5 of those different methods, but we've just done it spread out. And I don't think you guys realized we've literally done this problem 5 different ways now. I don't know, well, I guess 4. I don't think I ever did a Laplace transform on it, but I've done all the others, the guess and check, separable, linear. Here is a power series version. It was just kind of nice, I guess, to have that all in one video. So we know what the solution to this is. Y prime equals y. That's just y equals c e to the x. So what we're going to do here is solve it by a power series, get a general formula. We're going to write out a bunch of terms to make an approximation. Remember, like our solution here is y equals e to the x. You got this graphing calculator. Where's my calculator? There. Graphing calculators, any kind of calculator, any kind of computer software only knows 4 functions. It knows addition, subtraction, multiplication, and division. That's really all it has programmed into it. And everything else is based on that. So if I wanted to find e raised to the 0.5, this graphing calculator does this using a power series. E to the 0.5 would be right here, e raised to the 0.5. It has built into it here a power series, not the same one we're using, because this is a very slow method. It has a much more advanced algorithm, but it's literally just a bunch of powers of x. So that's how it calculates it. So everything we do in the real world is using power series, is using approximations. So we're going to approximate e to the 0.5. Y of 0 equals 1 here. So our solution is y equals e to the x, using 5 terms of our power series. Then we're going to do it using Euler's method. We're going to compare all 3. The actual solution, and when I mean actual, I mean the really good approximation the calculator gives us. This again is just an approximation. It's just accurate to like 9 decimal places. Euler's method and our power series. Okay, so here I wrote up a key to that entire thing. So here we're solving that power series. We get something that looks like this. Here is the solution. So go through these details. This is one you should be able to solve pretty easily. It's a pretty easy power series. You get x to the n over n factorial. Notice all these denominators are just my power. Like this would have been 4 times 3 times 2 times 1, 3 times 2 times 1, 2 times 1. Those are just factorials. That's x to the n over n factorial. That literally is the definition of e to the x. We take that, we may remember from Calc 2, that's the definition of e to the x. That's the Taylor series, technically the Maclaurin series because we're starting at 0, for e to the x. So if I take these first 5 terms and I just plug in a 0.5 for all of my x's, that's all I'm doing here. I'm not using this button on the calculator. I'm not using e to the x. I'm using these powers. I get this number right here. Then I could solve this by Euler's method. I'll show you in the spreadsheet how I did that, what I got. I get this. And then if I plug this in the calculator, I get this. So here are my 3 different possible answers. And then the question asked for find the error in each. I didn't bother writing that out, but we would take, Euler minus exact. There's our error. I did that backwards. Euler minus exact, our error. Power series minus exact, get our error. And notice, by the way, the power series is much closer. Okay, so I put all that in a spreadsheet because that's basically what we're doing in project 2. We're doing something exactly like that. Okay, so here's my actual, the first thing I did, let me walk you through step by step how I did this. Here are my x's. I want to start at 0 because that's the point we're expanding about, and we're looking for something near 0. We're looking for x equals 0.5, the y value for that. So equals 0. And now I could type all these out, but I can increment this by saying this value here equals the previous value plus 0.01. And then I could drag that down and generate as much as I want. Here are my actual solutions. So these are all going to be y values. So I know I'm starting at the point 0, 1. We're solving, say right here, y prime, or y of 0 equals 1. So equals 1. And now this value is going to be the x value, e raised to that x value. So what I'm really typing is this, e raised to my x value. The way you type that in Excel is the exponential of that x value. And then we grab this little corner here and drag that down as far as we need to go. Let's do power series next. So this, my starting point, this one I can just type in, or I can use the formula. I'll get the same thing either way. Now each x value or each y value is supposed to be using this formula. A0 is 1. It's my initial value, y of 0. So now I want 1 plus my x value squared over 2, and so forth. So this next one will equal 1 plus my x value. So I'm just going to click on it. Plus my x value squared divided by 2 plus, I done goofed, hold on, divided by 2 plus my x value cubed divided by 3 factorial is 6. And I keep going. My x value to the 4th divided by 4 factorial was 24, plus the x value to the 5th divided by 5 factorial was 120. Okay, yeah, I got the same thing. If you don't have your bars wide enough in Excel, it will round off what it's showing you. Even though it still has the entire value in its memory here, it rounds off what it shows you, and that can confuse you. So you want to make sure you have your bar wide enough so that you can see the whole thing. You want to be able to see a little bit of white space there. Let's make sure this one shows everything too. Okay, now Euler. So remember Euler's. We're just using linear approximation. Euler's is f of, say, xn is approximately equal to the previous one plus the derivative at the previous one times your change in x. So in this case, we have y prime equals x. That's a lie. Y prime equals y was our dE, given y of 0 equals 1. So my starting point, x0, is 0, y0 equals 1. That's my starting point. So I've got my x's, my y's, my y primes. Maybe I should put that in the other order. Because these y's here, these are the guys we're trying to find. So I start with 0, 1. My next point, if we're going by 0.01, will be 0.01. My derivative at that point be y prime equals the previous y value, 1. So my new y value, y at 0.01, will be the previous y value plus the derivative at the previous y value times my change in x. That'd be 1 plus, what was my derivative? 1 times my change in x, 0.01. So I think that's 1.01. Okay, that's what I've got typed in here in the Euler's method. So I start with my seed, the 0.01. Now this new value is going to equal the previous y value. So notice I'm going up a level here. This is where people go wrong with Euler. The previous y value plus the derivative. This one I have to type in the formula for. What is my derivative? Y prime equals y. So that's because of this formula was y prime equals y. I'm going to have that y in there again times my change in x, which is constant, 0.01. I'm going to start that over, make sure I typed. So this equals the previous, I think I was using the power series starting point, sorry. The previous y value right above me plus the derivative, which happens to be y, times change in x. And then I could drag that down. Yep. Yep. Okay. And then we would want to graph all of those. So when you actually do the project, you're going to graph all three of them, both near, and near meaning near our starting point. In this case, our starting point was 0, 1. So just using a few points. And then graph all of them at some far distance so we can see them diverge. Okay. I also want to do some more complicated power series. So most of the power series we've done just had a constant or maybe an X in front. I thought we would do one that has like a 1 plus X squared in the front of the DE. I've uploaded this document into Canvas, by the way. I saved this as a PDF and uploaded it. Okay, so at some point we're going to have to distribute here. So we start the same as we always do. Here's y. Here's y prime. Now look, I've got that x there that's hanging out in front of the y prime. So I don't need to worry about starting this guy at 1. Even though the n equals 0 term is 0, I'm going to bring this x in that's going to raise my power up to x to the n. So I don't want to mess with the y prime there. The y double prime, I'm going to have to distribute here. So I'm going to get an x squared times y double prime. That's going to fix this n minus 2. That's going to bring this up to x to the n. The x squared will. So I'm going to have a piece of this that I don't have to mess with, but then I'm also going to have this 1 times y double prime that I will need to mess with. So I'm going to write this guy out 2 different ways. And I'm going to use both of them. Because remember, the first 2 terms, if I plug in n equals 0, this is 0. If I plug in n equals 1, this is 0. So the first 2 terms are 0. I could, if I wanted to, start counting at 2. And I'm going to do it both ways. So I'm going to distribute here. That's this piece here. And notice I use this second version where I start counting at 2. And then x squared times y double prime. I use the first version because I know this x squared is going to fix my power. Even though the first 2 terms are 0, I don't care about that. Here's the negative 2x times y prime, and then 5 times y equals 0. Okay, so I fixed this one here by dropping this down by 2, bringing that down to 0, while simultaneously raising all of these up by 2. Now I start at 0 and my power is in. The x squared fixes that power, makes him in. The x fixes that power, makes him in. This guy already has in. Everybody starts at 0. Everybody has x to the n. So now I can squish all this together into one single sum. The only way a power series can equal 0 is if all the coefficients equal 0. So I just combined all these coefficients into one big giant coefficient equals 0. So here's my recursive formula. Remember, you don't have to write it like this. You don't have to solve for anything. This is it. This is the recursive formula. It's just easier to work with if you get the bigger one by itself. So I distributed here. You can check all my details. I spent like an hour writing this one up. So I think all the details are correct. I can't imagine there are any mistakes anywhere, but these are pretty nasty. So you guys check all my details. So we end up with this as our recursive formula, and I recopied it here just for convenience. This is second order. Second order, A0 and A1 are free. In fact, we know if we're solving an IVP, that's y of 0, that's y of 1. Or I totally lied. That's y of 0, that's y prime of 0. Okay, we start plugging in n equals 0, n equals 1, start plugging in numbers here. So if I plug in an n equals 0, this will give me A2. That will depend on A0. You can check all my arithmetic here. Same thing here. Now here, when I start plugging in bigger numbers, if I plug in a 2 here, I'll get A4 is negative A2. but I already know A2. So all of this turns out to be negative 1/4 A2. A2 I had up here. Remember, you have to keep going until you get back to A0 or A1. Everything will depend on A0 and A1. We only have two free parameters. So negative 1/4 times negative 5/2 is positive 5/8, A0. And so forth. I kept going all the way up to A8. Because I typed this DE into Wolfram Alpha, this is what the real solution looks like. There is a solution to this DE, but it depends on Legendre polynomials and Legendre polynomials of the second kind. This is a very, wow. There was a button here that said approximate form. I clicked that an hour and a half ago, and Wolfram Alpha is still thinking about it to try to get like a numerical solution here. So we're not going to have an exact form here unless you want to look up Legendre polynomials of this type. This is a very, very complicated one. But I did notice here that they gave me what some of our solution curves will look like. In particular, here's for y of 0 equals 1, 1 prime of 0 equals 0. So I said, well, okay, let's graph out our power series solution for this initial value problem and see if we get something that kind of looks like this. Now, they don't give me Wolfram Alpha here. It doesn't give me any numbers or a y-axis. I'm not even sure where the y-axis is here. And I don't have any kind of scale here, but I want to see if my solution at least kind of looks like this. So I'm going to solve that IVP, y of 0 equals 1, y prime of 0 equals 0. Every single time, y of 0 is A0, y prime of 0 is A1. So all my A1s are going to be 0. All these terms here, these are all going to be 0 in the final solution. I'm only going to have the A0 terms. So I didn't bother writing it out as two separate pieces since all of these, everybody that had an A1 disappears. A1 was 0. So here is my solution up to x to the 8th. Okay, I went ahead and threw that into some graphing software. That looks like this. Hey, that looks like their solution. See it? This is coming up. Our y-axis is back here somewhere. So it's going down and back up. Okay, that's what I'm getting. And then just to get more practice with plugging these into a spreadsheet, I type that into a spreadsheet as well. So let me show you what I did here. I'm going to retype this. Here are my X's, here are my Y's. So I'm starting at the point 0, 1. That's my seed. Each X value, I want to increase. I want to go by small increments. I'm going to go up by 0.01. So this will equal the previous value plus 0.01. And then I drag that down. I don't know, it looks like I went to, and until I reach X equals 1. I could keep going. I could go to 100 if I wanted to, but power series usually aren't good for very far away from your seed unless you keep a lot of terms. Okay, now what are my y values going to look like? My y values are going to be this polynomial. So I'm not going to type the whole thing out here, but I'm going to get started. 1, minus 5/2 x squared. So this will equal 1 minus 5/2, 5 divided by 2, times, you have to have this times here, my x value squared plus 5/8 x to the 4th. 5 divided by 8 times, if you don't put the times, it won't take it. And it'll yell at you. X to the 4th. And so forth. And I would keep typing. See, I typed out all the way up to x to the 8th here. Then once I get all these in, I drag these down. I mean, of course, I'm going to get different numbers here. I didn't keep as many terms. The more terms you keep, the more accurate it'll be. Notice, though, this is interesting. Here I went up to x to the 8th. Here I only went up to x to the 6th. These are almost identical. Remember, I'm plugging in like 0.11 to the 8th power. That's going to be a very, very small number. That's why these things converge. That's why we can do power series, because near zero, bigger and bigger powers of x near zero get really, really small fast. If I try to go up to 100 to the 8th power is gigantic. My error for all my left off terms is going to be huge. Okay, then once I get all my points, I can tell Excel to plot it. I like to highlight my 2 columns. And then we go to insert. And I like to use this one here, the scatter plot. Now, of course, on a project, you would want to go in and fix this, like label your x-axis, your y-axis. Everybody's version of Excel is a little different for editing graphs. Like I honestly don't even remember on this one. Over here on mine, I'm on a Mac and I have a particular version of Excel. Yours might be different, but I would want to put on a title, axis titles, everything, if you're turning this in as a project. So X and so forth. You know, I'm not going to make you sit and watch me go through all that. Okay. One last thing I wanted to mention today, covering a lot of stuff today. We keep expanding about x equals 0. We don't have to. Like, what if I wanted to solve this IVP here, but my initial points weren't y of 0 and y prime of 0? What if the IVP I was trying to solve was y of 25 equals 7, y prime of 25 equals 32, whatever? What if I wanted points near x equals 25? Then I wouldn't expand about 0. I would expand about the point 25. So here is an example. Remember, Paul's online notes is always great. Here's a good example where he expands about a non-zero point. In general, if you're expanding about a non-zero point, or even at 0, x 0 equals 0 still has the same form. This is what a general power series looks like. It has an x minus x naught to the end. So here he walks through an example of expanding about a non-zero, non-singular point. So you can read through that. And at the very end, when we get our solution, we'll have all these powers of x minus -2 or x plus 2. Then if I plug in points near x equals -2, this will give me a really good approximation of the real solution. This might not be any good near 0, but it would be really good near -2. Okay. Yeah, we've gone a really long time. Maybe I'll make up another video and post it as like a homework help. Yeah, I think I can find some spare time today because these other two homework questions might be a little more challenging than I originally realized. Yeah, I'll do that. All right, any questions? All right, stop the recording.